Hi guys, so today we are going to combine what we talked about at the end of last class with a new theorem called the rational zero theorem in order to factor and solve some polynomials that we have not been able to until this point. So the first one we're going to look at is actually going to be pretty similar to the last question from our notes last class. So the first thing we're going to do is we are going to prove that 1 is a 0. We're going to do that using synthetic division. Well, if 1 is a 0, then I should get 0 as a remainder when I do synthetic division. So remember, I've got 1, I fill in my 0 placeholder. I'm going to go ahead and do my synthetic division. Okay, and I do get 0 as a remainder. That right there is my proof. But what's more important about this is the remaining polynomial. So 1 is a 0. That means that x minus 1 is a factor. Then if I look at the remaining polynomial, I can then factor what polynomial is left over. So I can figure out what, remember, when a is 1, these are our fast questions that we need to get done quickly. What multiplies to negative 6 and adds to 1, plus 3 and minus 2. But again, since the original polynomial was not this, the original polynomial also had that 1, we also include that x minus 1 as a factor. So what we're going to do today, though, is we're going to figure out what do I do if it doesn't give me that line to start. And in order to do that, we're going to use something called the rational zero theorem. So the rational zero theorem is what's listed right here. Basically what this means, it's kind of summed up in this second box. But if you have a polynomial, all of the possible rational zeros can be found using the factors of the constant term and the factors of the leading coefficient. Now again, we're talking about possible and we're talking about rational. So remember, rational zeros do not include things like 3 plus the square root of 5. That is not a rational zero. So that it could be a zero of the polynomial. It won't come up in this theorem though. Something else, this also says possible. So every one of these is not going to work. Some of them will, some of them will not. So to find the possibilities, we start with p. P is the factors of the constant term. The constant is the number that doesn't have any x's. So in this case, the factors of my constant term, p, are going to be plus or minus 1, 2, 4, and 8. All of these are always going to be plus or minus because in this case it's a negative 8. So one of them will be plus and one of them will be minus. It doesn't matter which one's which. So we need to consider that both of them can always be plus or minus. All right, then we're going to move on and look at q. Q are the factors of the leading coefficient. Remember, that's the coefficient in front of the highest exponent term. So q here is going to be plus or minus 1, 2, and 4. So once we've found all those values, then all we do is we come up with the possibilities of p divided by q. So what we do is we take every p and we divide it by every q. So if I start with 1, 1 divided by 1 is 1. Then I do 1 divided by 2 and 1 divided by 4. Then I go to my next p-value. 2 divided by 1. Then I can do 2 divided by 2. But 2 divided by 2 is 1. That's already on my list. Then I can do 2 divided by 4. That's 1/2. That's already on my list. So then we move on to the next p-value, which is 4. Well, 4 divided by 1 is 4. 4 divided by 2, already on my list. 4 divided by 4, already on my list. Then I would move on to 8. 8 divided by 1, 8 divided by 2 is already there, and 8 divided by 4 is already there. So this final list of p over q values are all of the possible rational zeros. So these are basically the points that we're going to use to test with synthetic division and do the same process we did in the first example. All right, so you guys go ahead and pause the video and try B. So find your values of P, your values of Q, and all the combinations of P divided by Q. All right, so P here is just plus or minus 1 and plus and minus 5. Q, plus or minus 1, 2, 3, and 6. So then we move on to P divided by Q. So again, every P divided by every q. So that's going to give me 1, 1/2, 1/3, 1/6. Then I'll do 5 divided by 1, 5 divided by 2, 5 divided by 3, and 5 divided by 6. So in this case, there weren't any overlaps. So we have a lot of different possible combinations here. Okay, so now what we're going to do is we're going to combine this together with that synthetic division process to factor and solve polynomials. So while this could be a little bit tedious, it's not going to be too terrible of a process, but it can get a little tedious depending on which numbers you're going to pick. All right, so looking at this first one, again, it says to factor. If you can factor by grouping or using another method that we've used in this class, use it, okay? The rational root theorem is kind of like your Hail Mary, okay? It's what we do when nothing else works. We don't want to jump to it and use it every time because it's long and tedious. But if nothing else works, then that's what we have to do. All right, so let's go ahead and work on this one. So let's start with finding our possible rational zeros. So values of p are 1, 2, 3, and 6. Values of q are 1 and 2. So our possible zeros are going to be 1, 1/2, 2, 3, 3/2, and 6. So now what we have to do is the not fun part. We pick one of those numbers to start with, and we're going to do synthetic division, and we're going to see if we get 0 as a remainder. If you get 0 as a remainder, that's great, okay? If you don't, then we got to start all over again with a new number. All right, so let's start with an easy value to at least a test. Let's start with 1. So I'm going to list my coefficients, and I'm going to do synthetic division. And I get a remainder of -4, which means that 1 is not a 0 of this polynomial. So that means I got to try another number. Now remember, we could do plus or minus. What's nice about this, though, is there's more than one answer that'll work in this case. So we need to find one of the answers that does. Well, let's go ahead and let's just try 2. Again, list those coefficients. And then I get a 0 as a remainder. As soon as you get 0 as a remainder, that's good, okay? That tells you that 2 is a 0. That also tells you that x minus 2 is a factor. Well, now we look at the remaining polynomial. The remaining polynomial, 1 degree less, so 2x squared plus 5x minus 3. Well, that factors. So again, a is greater than 1 here, so we got to go through those extra steps. 1 multiplies to -6 and adds to 5. We split the middle into those two numbers. 2x comes out, minus 1 comes out, and I get 2x minus 1 and x plus 3. So those are the other factors that can go with the x minus 2. So that is the factored form of that polynomial. Now, what this also asks us to do is to find the zeros. Well, once we've factored it, that's pretty easy to do. If x minus 2 is a factor, x equals 2 is a 0. 2x minus 1, that would give me 1/2, and x plus 3, that gives me -3. So I have this factored, and I've found the zeros. All right, let's look at B. So if you want, you can do synthetic division, and you can do plus or minus all the factors of 27. But again, we talked about how the rational zero theorem, that's what we want to use last case, worst case scenario. This can factor without using the rational zero theorem. And if that's the case, factor it. All right, we know numbers that multiply to -27 and add to -6. Those numbers are -9 and 3. So this is going to factor. I'm going to go ahead and go through that longer process because it's a bigger variable. And then let's go ahead and factor. X squared comes out. 3 comes out. So x squared plus 3 and x squared minus 9. Now it's not fully factored because I have a difference of squares. And now I have my fully factored answer. Well, now remember, it also tells us to find the zeros. Okay, now this is something that we've done back in quadratics. Well, 2 of them are easy, -3 and 3. But remember, we also have to solve and set this equal to 0 to get my other zeros. So I would get x squared equals negative 3. I would square root both sides. And remember, when you square root, first of all, we need to include plus or minus. And whenever we square root a negative, remember that becomes an I outside of the square root. So I have these 4 solutions right here. All right, let's try a couple more. So let's look at the next one. So same process. Let's see if we can factor it another way. We really can't. So what we're going to do is we're going to do our P over Q's. Now this one's pretty nice because your Q value is just 1. So we really don't need to do P and Q. It's really just going to be the factors of P. So the factors of 24. So it gives us a big list of numbers to try. So we get a lot of possible. All right, so we can guess any of these. I'm just going to take a shot in the dark here and go with 3. So I'm going to write my coefficients. There are no zeros skipped that we have to worry about. And I end up with a remainder of 0. So 3 works, so that's good. The problem here, though, again, our remainder is going to start 1 degree less than the original. Well, 1 degree less than the original, this was to the 4th. So this is going to be now x cubed minus x squared minus 10x minus 8. So it's not quadratic. It also doesn't work with grouping. So in order to get another 0, we have to go through this process again. Now the nice thing though here, my p-value is no longer 24, my p-value is just 8. So that's going to give me a lot less values to choose from. So I'm not going to have to worry about 3 or 6 or 12 or 24 anymore. So I've got a lot less options to pick from. But again, we just kind of have to guess. And again, there's more than one right one that could work for these, but we'll just take a guess. I'm going to go with negative 1. So I'll write my new coefficients. Okay, I'm not using the original. If I go back to the original, it's not going to help get this to a lower degree. My goal is to get this down to a quadratic, so I'm using the answers that I just got. So we'll do our synthetic division, and I get 0 as a remainder. So since I get 0 as a remainder, again, that means that 3 was a 0, and negative 1 is also a 0. Now our remaining function is down to a quadratic. That's a quadratic that we can factor. So we'll go ahead and factor that. A was 1, so that's an easy, quick factor. Multiplies to negative 8 and adds to negative 2. Then we also include the other 2 factors that we know based on getting 0 as a remainder. So x plus 1 and x minus 3. So this is the fully factored form of our original equation. Now, if I also wanted to find the zeros, I could. My zeros would be 4, negative 2, negative 1, and 3. So those are all the numbers that would have worked in synthetic division. So let's say I didn't pick 3 from the start, but I picked 4, or negative 2, or negative 1 the very first time. Any of those other numbers could have worked, so I didn't have to get 3. I could have gotten any of those numbers. All right, so now we're just going to focus, instead of factoring, on just finding our zeros. So one thing you may have noticed in the questions we've done so far, the degree of the polynomial was the same as the number of solutions that we got. And that follows something called the fundamental theorem of algebra. So if we have a polynomial of degree 5, it's going to have 5 zeros. As long as we consider complex solutions, and we consider multiplicities as being multiple solutions. And remember, multiplicities is like if a factor is on there twice. So x minus 3 squared, we would count that as 2 solutions in our total count to get to the degree. All right, so let's look at this first example. Again, we only use the rational root theorem when absolutely necessary. X cubed minus 64 is something that you can factor. It's something we did last class. It's a difference of cubes. So this factors into a binomial, and then we use scums to get the trinomial. Square the first, change the sign, multiply, and square the last. So now all we have to do is find the zeros. Well, it says all zeros, which means potentially complex. Well, if this was x cubed, we're going to have 3 zeros. One of those zeros is easy. It's x equals 4. The other 2 zeros are going to come from the resulting trinomial. That doesn't factor because it's not going to give us real solutions. So since it's quadratic, we need to use another method for quadratics that we learned last semester, which would be either completing the square or quadratic formula. I'm going to go ahead and use quadratic formula because that's what more of you tend to use. So negative b plus or minus the square root of b squared minus 4ac all over 2a. So let's go ahead and simplify. So that's 16 minus 64, which is a negative 48. And remember, we cannot simplify the negative 4 and the 2 yet. We have to simplify what's under the square root first. So square root of 48 can simplify into 4i root 3. Then, since all of those numbers are divisible by 2, we can divide each of those numbers by 2. And that gives us negative 2 plus or minus 2i root 3. So now we have 3 answers for our third degree polynomial. X equals 4, negative 2 plus 2i root 3, and negative 2 minus 2i root 3. All right, if you feel pretty comfortable, go ahead and try the next one on your own. This is something that we saw back when we were doing quadratics, so it's something you might be familiar with. All right, so on B, that is a difference of squares. So we can factor this on our own using the methods we're used to factoring with. X squared minus 4, x squared plus 4. X squared minus 4 factors into x plus 2, x minus 2. X squared plus 4 does not factor any farther. So now let's find our zeros. This was a 4th degree polynomial, so we're going to have 4 zeros. So I've got negative 2, positive 2, and then I'm going to solve x squared plus 4 equals 0. So x squared equals negative 4, square root both sides, and that's going to be plus or minus 2i. All right, so now let's look at some that may not factor from that first step. All right, so look at C. We can try grouping, but grouping isn't really going to work out for us. So since grouping's not going to work and there's 4 terms, we're going to have to use the rational root theorem. Well, the good news here again, our q value is 1. So at least our p over q's are just going to be the factors of 12. So 1, 2, 3, 4, 6, and 12. And then again, at this point, we really just kind of have to take a guess and just keep going until we get one that works. So like, let's say I start with 1. 1 isn't going to work. But sometimes we got to try some wrong ones until we can get one that does work. All right, so since 1 doesn't work, let's go ahead and try another number. I'm just going to try 3. I happen to know that that one may work for us. So we write our coefficients. And I get 0's remainder. 0's remainder is good. That means 3 is one of my zeros. This was x cubed, so there's going to be 3 of them. One of them is 3. Well, now let's look at the resulting polynomial. It's quadratic, but this time it's a quadratic that doesn't factor. So very similar to what we did with A, then on example 5a, we need to use another method to solve this quadratic. Whether that's completing the square or quadratic formula is up to you, but we do need to solve this. I'm going to go ahead and do completing the square this time, just because it's a good review. So I'm going to do x squared minus 2x plus blank, move the 4 to the other side. My number that goes in the blank is the b value divided by 2 squared. It goes in the blank on both sides. That is a perfect square trinomial. Factors into x minus 1 squared. Square root both sides. So x minus 1 equals plus or minus the square root of 5. So x equals 1 plus or minus the square root of 5. So again, I have three solutions. 1 plus the square root of 5, 1 minus the square root of 5, and x equals 3. Don't forget about the very first answer that you got whenever you did your synthetic division. All right, so now moving on to D. Again, use methods that you already know first. We do not have to use our synthetic division process in our P over Qs on this one. First of all, you may notice there isn't a constant. Well, that's because you have a GCF. And again, when it comes to factoring, our first step is to always take our GCF, which in this case is x. So before we do anything, we're going to take out the x. Then let's see if this will work by grouping, and it does. So we don't need to go through that whole P over Q process with the factors of 16. All we need to do is regular old grouping like we've been doing all along. X cubed comes out. I'm left with x minus 2. Then I've got a plus 8 that comes out. I'm left with x minus 2. So out of this, my parentheses that match is x minus 2. What's left over in the purple part is x cubed plus 8. So now it's factored as far, we can go ahead and factor that sum of cubes as well. So let's factor that sum of cubes. That's going to be x plus 2. And then we're going to use the SCUMS acronym. Square the first, change the sign, multiply, square the last. All right, now let's go and find our zeros. So one of those is x equals 0. X equals 2. X equals negative 2. So I already have 3 of my answers. Because the original was a 5th degree, I'm going to have 5 answers. Well, let's go ahead and use a different quadratic method to get my 2 remaining answers that go with this. So again, I'll do completing the square again just because I think it's honestly a little bit faster, but that's just my preference. It's also pretty similar to the one we just did. So I'm going to add negative 2 divided by 2 squared. So I'm going to put 1 in both sides. That factors into x minus 1 squared. And negative 3. Square root. This is going to be I root 3. Add the 1. And I get my other 2 solutions. So 5 total solutions, 2 of them imaginary, but I do still end up with my same total number of solutions. All right, so again, the biggest thing to take away from this, don't forget the methods that you guys have already learned for factoring and solving quadratics. It's going to save you a lot of time and you don't have to go through this P over Q process when you don't need to.